Hi, I'm Daniel Lee. I hope you're here because you want to see how ODEs work in Stan. If that's not what you want to do, you can leave. That's okay. I won't be offended at all. By the way, this material is kind of new. I ran through all the code this morning, so it works. But there might be a little hiccups, but hopefully you'll forgive me, and we'll learn a bunch of stuff. So quickly, before we begin, the overall structure, it's going to be pretty fast. We have an hour and a half. What we're going to try to do is do 4 separate things that all build on top of each other. The first is write an ODE in Stan and simulate from that ODE. The second is estimate the parameters of that ODE from a single set of observations. Third is estimate it from multiple sets of observations. And why we want to do that is so we can get into parallelization. I'm assuming a lot of people are curious about how to write things so we can be parallelized. That's where we want to end up. Any questions so far? What you should be comfortable with is writing Stan programs. We can't cover all of that here today, so hopefully you've already seen functions. Hopefully you know how to run Stan from an interface of your choice. For this course today, we're going to be using command Stan to run Stan. The reason is it's easier to enable parallelization for the time being. Right now, parallelization isn't really available through RStan or PyStan, so it's best to get into the lowest level interface that's possible. And we'll be using RStan for exporting data and reading the fits. Something that's important is that you should have some familiarity with the Stan program blocks and Stan types. So if that goes a little too fast, please ask me to stop, because the way you're going to gain out of this is to figure out what you don't know. What we don't have time to cover, we won't go through a full tutorial in Bayesian inference, or Stan, or ODEs, or expert level debugging through ODEs. This is actually just going to be a very quick guide through ODEs. Some quick notes. We're going to work with a very simple example. It's going to be the simple harmonic oscillator. It's in the Stan manual, so if you get lost today, no problem. Just go look at the Stan manual and it's there. Why I'm doing this is because we want to highlight the mechanics of ordinary differential equations in Stan and not get bogged down with trying to solve for a complex ODE. If you want to use your own example, that's fine. But while we're here, we'll try to go through a simple example so we can work on the rest of all the scaffolding that needs to go with ODEs. To get the most out of this next hour and a half, first, if you can, work together. If you're sitting next to somebody, make friends, do pair programming. And the second thing is ask questions whenever, whatever. The responses I'll give are either an answer or something like I don't know, or I'll tell you later. Those are the 3 answers I can give. All right, so the last thing before we start, install command Stan version 2.18.0. So go ahead and download the latest command Stan, and also clone this, repository or download the files there. How many have installed command Stan before? So 3, 4, 5. Okay. How many use RStan? Okay. PyStan? All right.
Are we going to take a few minutes to do this?
Yeah.
Yeah, does anybody need help doing this? Anything here?
Perhaps in 2 minutes.
Yeah, okay. Yeah, this is something to do.
Are there any designated places with all outlets? Sadly, I can only use my laptop when I have access to.
There's power down here,
Okay.
so you have to sit in the front.
I think each row has 12 outlets.
Oh. No, it's okay.
So everyone download the command stand tarball? Yeah. Still downloading? What about the workshop materials? You don't absolutely need them, but they make things go a little faster, I think. How many people in here already write ODEs in Stan? Oh, awesome. Just out of curiosity, what sort of applications are you using it for?
Biological.
Biological? Anyone outside of biological? No? Okay, cool.
Guts, yeah.
Hmm?
Blood and guts.
Okay. All right, while everyone's doing that, we'll just get started. We'll start by writing ODEs in Stan. So what's an ODE? Just quickly, it's a differential equation describing the derivatives of a function with respect to an independent variable. So what does that mean for us? There's an independent variable t. It's usually time, but it can be anything else. There's some sort of independent variable y, or sorry, that's a dependent variable y that depends on t. So that's what we're looking for. We want y of t for some set of t, but we don't know how to compute it directly. If we knew how to compute it directly, for example, if you knew an analytic form of the ODE solution, you should use that instead. But here we don't know what that is. What we have is a function that describes the derivative of the dependent variable with respect to the independent variable. So what we have here is f prime of t, so that's dy of t with respect to dt, right? And that's some function of t, the time, x, whatever data you have, and theta, whatever parameters are in the model, right? So with that, you have a function that describes the derivative. So the example we're going to use is a simple harmonic oscillator. It has two states. There's an equilibrium position 0, 0. And what this thing does is there's a restoring force proportional to the displacement. So this thing starts at 1, 0, which is here. And it's going to want to move towards 0. So it'll follow this trajectory around, right, over time. Okay? And the differential equations here are the derivative with respect to time for the first component is y2, and the derivative with respect to the second component is minus y1, the distance away from 0, 0, minus theta times y2, where theta is some constant value. If we knew the initial conditions, so the starting states of y1 and y2 at time 0 and theta, we can go ahead and solve for each time point, t0, t1, t2, t3. Right? And we can get the values of y1 and y2 at those time points. That's what we're looking for. Questions so far? More background? No? So we'll get into how we can implement this in Stan. So the Stan function for ODEs must have the signature. It has to be strict. It has to match this thing exactly. So it has to return a real array. There's a function name. This can be called anything. These argument names are not important. What's important are the signature itself. So the first is real, and that's for the independent variable. Then the actual states at that time, the parameters that you're interested in. So these are going to be dependent on parameters in your model. This is data. So these are going to only depend on things inside the data blocks. And xi, int xi is an array of things that are also data but integer data. Okay? So for this example, which is just what I outlined before, this is how I would write it. So here's a real array. There's a simple harmonic oscillator, the function named show. There's t, the time, y, theta, xr, xi. So that always has to be there. dy1 dt is just y2, that expression there. dy2 dt is minus y1 minus theta of the first, since this is an array, I'm pulling out the first value and putting it there, times y2, right? And I'm returning the value of the derivatives of the two states at that time. So you can have this be as many states as you want, you just need to return back the derivatives of the states at that time, right? This here doesn't have any expression that involves t, but it can also have some expression that involves t. Yeah. Questions? No questions? All right, so if we're to break it down, the number of states, once again, is 2. We have a y1 and a y2, right? So that's the number of states. That means we have to return back in a real array of 2 elements, right? So the states have to match the number of derivatives we return back. And the return value is the function, is the value of the derivative evaluated at that time, conditioned on the state that you know. The arguments are t, an independent variable, theta. So once again, these are ODE arguments that depend on the parameters. So parameters in the Stan model block. Right. XR are ODE arguments that depend only on data, so things in the data and transform data block. And XI is dependent only on data, since we only have integer data. There are 2 integrate ODE functions that we have in Stan, BDF and RK45. And these functions, when you use them, they'll give you back the solutions of the states at the times you specified. So BDF is for the backward differentiation formula, and this is for stiff systems. And the RK45 is for, did I get that backwards? For non-stiff? No, for non-stiff systems. Right, and they take the same argument, so you're able to swap out just the underscore BDF with underscore RK45 if you want, and there's no problem. The function signature of the integrate ODE functions are, it returns back in a real array. It has an ODE function that you specify, that's the name of the function. It has the real initial states, so this is where you start. It has the time that you start. It has the times that you're interested in integrating over. It has the theta, the arguments that are based on model parameters. It has arguments that are based on the data and integer. So if you've gotten command Stan, and hopefully it's, you know, the Stan ODE workshop materials is in a directory that's kind of adjacent to it. If not, wherever it is, we can go ahead and make this show sim executable. Does anyone want to do that? So it would look something like this. I've already built it, and we can look at it. So hopefully this is what you have inside your directory. Can everyone see that? Is that big enough? Yep. All right. The ODE function is exactly what I wrote out. What we have in here is transform data. So I picked 20 times that I'm interested in. 1, 2, 3, all the way up to 20. The initial conditions I set at 1, 0. Theta 1 set as minus 0.15. And there's no real data that needs to go inside this expression, and there's no integer data that needs to go inside that expression. My model has nothing to do with this ODE, right? So we can use this ODE function anywhere in generated quantities, transform data, transform parameters inside the model block. And here, I'm just generating from here, from this ODE. So, anyone have an idea what this is going to do if I run this code?
Presumably integrate the system from 0 to 20.
Yeah. But there's not going to be any noise. And for every iteration of this model, it's still going to try to do Bayesian inference over P, which is, there's no prior. It's just between 0 and 1. So I'll get different values of P, but along with that, I'm going to get 40 different values. And it's just going to have the ODE solution again and again. Right? Does that make sense?
Where are you using the P?
We're not using the P.
Oh, okay.
So it doesn't factor into the model at all, into the ODE solving at all. You can just tack this on anywhere.
So is that needed just because the parameter block can be empty?
Technically, the parameter block can be empty, but you have to use a different algorithm. There's a fixed param algorithm that will initialize things to whatever and then just run. But with that P in there, I can just run this like any other Stan program. So if you're not used to using command Stan, let me make this a little bigger. When I type the make command from my command Stan folder, what I'm doing is I'm building an executable. And from this folder, which is where the file is, I'm going to run it, and I'm going to ask it to sample. So what it's going to do is it runs Stan. Okay? And if I go ahead and read that output, what I have is for every iteration, I'm doing 1,000 posterior draws. So for every one of those posterior draws, I'm running this function integrate ODE BDF and getting out the solutions. So if I look at y1, comma, this is the solution that I get. If I look at the second iteration, it's actually producing the exact same thing. Right. So this is kind of wasteful, but it's simulating from that ODE. We can look at this real quick. And there we go, right? So that's what it's doing. So since you're sitting there, let's adjust the program so it accepts data. It accepts the times as data, and then also add noise to the generation process. Okay.
I never downloaded the example. Sorry.
Yep.
So can we use everything else from our Stan except for the parallelization at the end?
Yes, absolutely.
Because with installing command Stan right now is actually complex.
It's probably easier than you think.
On Windows?
On Windows, yeah, it should just be make build. That's okay. Oh, I should ask that. How many people are on Windows? So it's most of the room. Unfortunately, Windows, to get parallelization working in Windows, it's a lot harder than it is on Mac or Linux. Just letting you know. If you're on Windows, you have to type in the .exe at the end. Is anybody stuck? Need help? Questions?
Should I try to add normal RNG inside the simulation function?
Yes.
What kind of arguments does it take?
Hmm?
Does it take 2 arguments?
Takes 2 arguments, the meaning and the standard.
The weird thing about that is it's not factorized, so like you have to do like LIF, so there's like 20 about 2 outputs, so you have to like move over all of them instead of just like lumping it all in there. Yeah. But yeah, that's the right thing.
Yes.
So command scan is taking like an extremely long time to compile even that first example. Is that expected? Like 5 minutes plus?
The first time you compile it, you're on a Windows machine? Linux. So the first time you compile it, it'll take a long time because it's building the Stan compiler. So if you install rstan or pystan, it usually comes with a binary. So that's already pre-packaged for you. Command stan doesn't package anything. After that, subsequent builds should be pretty fast. By pretty fast, we're talking about so this first part translates Stan to C++, and that's pretty much instantaneously. This happens in rstan, pystan, doesn't matter what stan. And then this part here is the part that takes time. And so it's actually, if you sat through Bob and Sean's tutorial, it's going and instantiating all the functions that it needs using the math library and going. So it takes, is that 30 seconds-ish? All right, if you want to jumpstart, there's a file called show_sim_with_noise.stan, and that has most of what you need.
What I tried to do before was to put the normal random number generator within the function. Would that have worked?
In here, or
Like within, because we didn't really understand, so we were putting it into the derivative evolution.
yeah. So
Would that have worked, or would that?
no, that would not have worked. So the question here is, could you put the random number generator inside the derivative? And the answer is no. That'd be What is that? Is that a stochastic ODE? What we're describing in the ODE function is a derivative. That's it. It shouldn't be stochastic. It's a function. If you give it the same inputs, it should always return the same outputs. And what you're trying to do here is after you solve for the states, then we're going to add noise to the states themselves.
Like kind of you're measuring it, but not precisely.
Yes, exactly.
So what, I will never be able to make stochastic functions.
Bob, will we ever be able to do stochastic functions? I don't even.
I think I would defer that to Yi. We're gonna have differential algebraic equations, but like, I don't even know what those are.
Yeah.
So there's some kind of like, yeah.
Yeah. So the answer is we don't know.
Maybe. It's one of the things that we propose to look at as part of a grant proposal that we're doing with Metro, along with partial differential equations. We're probably gonna launch a framework to drop partial differential equation solvers into Stan as soon as we work out the details, but stochastic diffie-keys, I don't think we know how to do that yet.
I guess you could do this with explicitly having flattened variables for the noise. That feels like you could do something with this that and probably link your own solver or something. So I think like in principle if you really need it. But
You could write Euler, a simple Euler.
And then do stochastic. You could move forward, well, it depends what you're trying to do, but you can move the parameters forward in time using Brownian motion or sort of like a mean reversing or something like that.
So if I run this now, the output is going to have, for each row, it'll have a different realization of the ODE, right? So it'll have, y hat will have different noise. So it'll be close, but it won't be exactly the same. Okay. So if I go like, I'm reading that output. And y hat. Hat 1, then right, so those are all different realizations. Every single row inside that output is going to have a different realization just because we're adding different random noise to it. If you want to skip ahead, I've already generated the data and it's in this file called show.data.r. So it's here. So it's this file here. Everyone comfortable so far with the idea that you can solve for the states and we can simulate from this ODE? It's only going to get more complicated and faster. All right, so some quick questions. Can the ODE be discontinuous? Anyone know?
Discontinuous in what?
In the ODE parameter, like the derivatives are. So the answer is actually kind of. An example of this is if you're looking at like a pharmacometric example and you're looking at some sort of dosing mechanism, the dose stops at some point and then it becomes a different ODE. All you have to do is inside your ODE function, like here, say something like if t is greater than some value, right, like end of dose, let's say it's 10, then it's something else, right? So you can do something like that. So it's possible, you just have to be kind of careful. Can a model have more than one differential equation? You can have as many ODEs as you want. You're just going to solve for the states, so they're kind of independent.
Just on the earlier point, in this case, there's no problem with the gradient being broken in some way by the discontinuity that it gives.
Could you repeat that question?
I was under the impression that normally if there was this kind of if statement in there could pose problems with the gradient calculations, but it's obviously working with them somehow.
Yeah, so what's going to end up happening is that you're solving for the states, right? And the states may or may not be on that discontinuous boundary. And what we're trying to do is accurately solve for the states and get the derivative with respect to the parameters. You're specifying it with respect to time, not the parameters. So it's tricky. We need the solver to take small enough steps so it doesn't like skip over that discontinuity. That's essentially what it comes down to. And there are ways to control for that. We won't get into too much detail, but yeah.
Do I understand it correctly that discontinuity in the equation for the derivative doesn't necessarily imply a discontinuity in the density?
Yes. Yeah. Yeah.
Let me just add that I'd be super careful there. There's definitely ways to make it so that things do blow up.
Absolutely.
Like your fear of creating something that's not differential is totally valid. Like it could be a big problem.
And if you can solve the ODE analytically, you should go ahead and do that every time. It'll be a lot faster. Okay, so we'll get into estimating from a single observation, right? So we're now going to write a Stan program to fit the data. So what should be estimated? There's a sigma, the noise term that we used. You may or may not want to estimate that. There's this theta variable inside the ODE that we're actually interested in, and maybe possibly fitting so that we estimate the initial conditions. We can do that. Yeah. So go ahead and write a Stan program to fit it. Just a hint, most of the code should look very similar.
Daniel, why are you using BDF here if it's not a stiff system?
That's a good question. So the question is, why am I using BDF when it's not a stiff system? No other reason than things get stiff quickly. So something I'll mention a little bit later is that the ODE system that you describe here is not the system that we're actually solving for. We're actually solving this plus the sensitivities. And so that whole system needs to be stiff or non-stiff for you to use the right.
Okay, so you're using CVOD
S.
X.
Yes. Yep. Yeah, so for me, the default is always just using BDF.
Me too, but
Yep. RK45 kind of chokes when it gets stiff, and it's the derivatives with respect to the parameters that can also get stiff. How many people want more time? Okay.
I have a question.
Yep.
What is this 0.0 in the integrated ODE?
In the where?
In the integrate ODE, now the
Aha.
which is 0.0.
Good question. So the first argument is the name of the function. The second argument is the initial state. This is the initial time. So we're starting at time 0. And then t's are the rest of the times. Theta is the parameters that depend on the parameter block. XR is things that depend on data, and XI is things that depend on data.
So we could have written T0 instead of 0.0, right?
That's right. So we could have easily done,
I think it's in the data block already.
it's already in the data block. Oh, yes. Yep.
You estimate the y0, right? So why is it not in the parameter section?
In this model, I haven't. So let's quickly, well, let's walk through this real quickly, and then we'll change it so that it estimates y0 as well. So the functions block, the simple harmonic oscillator is the same. In the data block, we're reading in t, the number of time points, t0, where we're starting, t's, the different time points that we're interested in, y hat. So we're assuming that this y hat, this observation, aligns with the times that we have, right? That's sort of the assumption that we're making. And then for right now, y0 is passed in as data. For transform data, we have nothing in XR and XI, but we still need to pass it into the function. So that's why these are here. For parameters, we're estimating theta, just this one value, and sigma, which is the noise parameter. Right, and we could run this. If we wanted to also estimate the initial conditions, all we have to do is move this to here. Right, and it's that easy, I think.
I tend to agree though, like it's strange that there's the sampling statement for y0 in the model blocks, it's not influencing any parameters, it's not inferred, it's just gonna add like a constant log density.
That's right.
Right.
Right, so
Yeah.
so this statement when y0 is data does absolutely nothing, right?
Well, because there's no parameter.
Yeah. It's a constant. Yep. So if I run it, it's running, takes a little longer. If you were to do this analytically, it's much faster. Okay, while we're waiting for that, just some more specifics about this integrate underscore function. The times, so what I didn't mention was that the times must be sorted. They have to come in order. So time, the first element of time has to be smaller than the second, third. I believe that they can't have duplicates right now. That might be something that we can relax later, but right now everything has to be strictly ordered. Yes?
They have to be like evenly spaced?
No. Nothing about evenly spacing, it's just that the first value has to be smaller than the second. And each of the times must be greater than t0, right? So right now we can't put in the initial condition point inside the ODE integrate as a time value. What that means is that my t0 is 0.0. I can't also have 0.0 inside my times. It just has to be something greater than 0. The times can't be parameters now, so it has to be data. We can't solve for what time this thing was at, right? XR and XI must be data only. XI is by definition, you can't have integers that are parameters, but XR must be data only. There are 3 optional parameters at the end that we haven't discussed, and once you include one, you have to include them all. And these are passed to the solvers themselves, so the integration methods in CVODEs and Boost. So the first is the relative tolerance, and that's defaulting at e to the minus 10, absolute tolerance, and the max steps. So as you're debugging, one of the things that I do is set the max steps pretty low, just to make sure that I get out of bad parameter spaces. So what ends up happening is even though your system may not be stiff, if you pick really wonky parameter values and start in a very, very bad place, the solver is going to take forever to try to estimate those states. And so as you're building up the model, you might relax some of these conditions, put tighter priors until you can get it reliable, and then start getting the tolerances back to where you need them to be. All right, so this thing should have finished. You can kind of see the fit happening. Yep. By the way, I think in the data set that I generated, I put in the wrong data value. I'm pretty sure it's 0.15 was how I generated it. Okay. So some more implementation details. Just to get into it a little bit, what we've written in our function is dy dt. And we're solving for y at those time points that we specify. So we're getting y at time 1, time 2, time t. And we're solving for that state numerically. We're using CVODEs under the hood and Boost when we do RK45. But in Stan, what we actually need is not only those states, but we need the gradients with respect to the parameters of the model. So that means we also need dy of that time point d theta for all the theta that it involves, right? So the ODE system that we're actually solving in Stan has many, many more states. So it's the number of states in the ODE system times the number of parameters in the theta block. So if you're looking to, the complexity of this ODE system depends on the number of states you're solving for times the number of parameters you have in theta. If we also need to solve for the initial conditions, we also need to account for number of thetas. So add another, we need the dy0 d theta for everything. Any questions? Okay. So next, we'll go into estimating from multiple observations. For anyone that deals with data, you probably don't have just one observation. You probably have multiple. We'll go through this, and then hopefully we can get to parallelizing this. So let's update the simulation first. Instead of one set of observations, let's draw 10. So write a simulation program that'll draw 10 thetas, then generate observations from them. Yep. If you want a head start, look at show_multiple.data.r. Or sorry, that's the file. So this is show sim with noise_multiple.stan. Sorry, this one actually doesn't have it. Oh no, it does. So if anyone's looking at this show sim with noise multiple.stan, and it doesn't look very different from the other simulation code, right? The difference here is that there's a parameter theta, and I've just added a prior on theta, right? So it's going to draw random numbers of theta, and then I'm doing the same thing. And if I look at different rows of the output, so each posterior draw is just going to be a different data set, right? It'll have a different value of theta. It would have simulated forward using that value of theta and then added random noise on top of that. Does that make sense? Yep. So. Takes, very little time to generate. Let me make sure I do this right. So if you're curious how I'm generating the actual data set from within R, I've set a seed. This is an rstan function that will read the output of command stan in a file called output.csv and create a stan fit object that everyone's used to. So that. So if I look at fit, it's this. What I want to do is I want to extract the y hats out of here. So there are 1,000 posterior draws. 20 by 2, that's what we want. And I'm just going to pick n is 10. I'm just going to sample from the rows of y hat. I'm just going to pick 10 of them. So IDX is this. And then I'm just going to construct a data set that has the t as 20, n as 10, the times is 1 to 20, times 0 is 0. The y naughts are going to be just 1, 0. And then y hat, I'm just going to pick the ones in the index. And that's how I generate this show multiple.data.r. Questions? Okay. So the next exercise is to extend show underscore fit.stand to fit to the multiple observations. And one of the hints is that you'll want to loop over each individual. Sorry, that should be run with init equals 0. You might need that. Yep.
A couple of them in the standard parameters block there of the multiple dot stand, yeah. In the for loop, why there are no indices for the y in the square brackets?
Why there are no, so the question is inside the transform parameters, as I'm assigning this, why are there no indices in here?
Yes.
The reason is that this integrate ODE BDF, if you look on this side, we know that it's supposed to return back a real y comma, yt comma 2. The structure is that, right? And here we have another index. So we're going to slice into this array structure and just assign these two things, the nth value, the t by 2 structure that's inside the nth value with the integrate ODE BDF.
Okay.
Does that make sense? So there are just in the original with the single observation, there's just one t by 2 array, and when they're n, we just have n of those.
Okay.
I believe I could have done this. Bob, would this have been legal on the right side if I did that?
So is it a yn equal?
Yep.
Yeah.
Instead of this,
Yes.
right? So I could have done that instead, which may be a little clearer. Yep.
The previous example, y was an array dimensions b by 2. Could it also be a matrix dimensions 2 by b, or it has the same layout in memory but different data type?
Good question. So the question is the return type or the output, or sorry, the type that we've declared is a real array of t by 2, and can we make this a matrix? The answer is no. It's strictly typed. So this function here will return a t by 2 real array. Now that doesn't mean you can't do it as a matrix. We could have done this instead, like equals matrix y. Right, and in fact, I don't even need to do that. I could have done this instead. And so that'll convert a two-dimensional array into a matrix structure.
And semantically, is this a cast, or that's the data copy?
It's a copy. It's a copy, but the cost of these copies are pretty negligible relative to the cost of solving an ODE, so it's fine in most cases. Oh, sorry. To do this correctly, it would have to be matrix t by 2, like that. Just to make sure. So hopefully you can see this. This is the function signature that I would be using, and it would just convert it. Okay. So hopefully you got to this point. There's a show fit multiple.stan that has the multiple fitting to multiple observations. The difference here isn't that big. Instead of having one theta, we have n thetas. The other big difference is inside our transform parameters. For each of our observations, we're looping over and doing this integrate ODE BDF. Right. And then in the same way, for our model, we have to loop over the model, or loop over each of the individuals. There are probably other clever ways to not have to loop, but for this example, this is probably straightforward. Yes?
Yeah, you can just use 2 vector there, right? Y hat n.
Yeah. So what Bob's suggesting is 2 vector out here, y hat Just y hat? Can we do that? Will that n?
Well, no, I guess it would just be,
Just flatten the whole thing.
yeah, no, that's not gonna work.
No. Well, if we flatten the whole thing, it would work. But
Yeah, inside there, you could do 2 vector y hat in, twiddle normal, 2 vector y in. Don't think it's gonna be any more efficient though.
so the question?
My question was related actually with that. How more efficient is when you use for loop for this kind of computing livelihood instead of one-liners? I mean the other way around. How a one-liner is more effective compared to a for loop?
So I think this is actually a vectorized statement here. This is not. I think this is what you
Yes.
is typically asking for. The best way to figure out is to time it. But in general, the above loop is going to be faster. In this case, it's because in the computation of the normal LPDF, there's a log sigma that happens. And in this case, since it's a constant, it doesn't even matter. But in other cases where, actually sigma is a variable, so it'll have to do log sigma t times n times. And in this thing, it'll just have to do it n times, well, n times 2, because we do it twice.
Yeah, it also reduces the size of the expression graph, which is good because it cuts down on the number of virtual function calls. And it can reduce the memory requirements because there's an implicit addition here every time you use a twiddle that gets added to the target, and that winds up building a big expression graph of plus, plus, plus. That all gets compressed in the vectorized statements. But that's just the vectorized distribution functions. Everything else is going to vary. Loops themselves are very fast in STAN. It's not a loop problem. It's that you're doing extra auto-diff operations when things aren't vectorized because we have some clever functions that compress the auto-diff. So if everything's a double value, like in generated quantities, loops will be just as fast as vectorized things. So it's not like R where you pay a huge penalty for loops.
Okay, so it's still going, but it's fitting. And we'll take a look at that in a second. Just a quick review, the ODE function is the same. Whether we did simulation, fitting to one set of observation, fitting to multiple sets of observations, you write it once and that's it, no problem. ODEs are just part of the model, right? So they're not we build a statistical model on top. We're saying that there's some measurement process that happened here. There was some random noise that got injected. We injected it, in real life, there are other reasons for statistical models. And what we're doing is we're estimating the parameters of the model simultaneously with the parameters of the ODE. They're just part of the model. Everyone good so far? Do you feel like you could have done this, like taking that progression, going from simulating it from an ODE to fitting an ODE to go into multiple patients? Yep. Good, because parallelization just adds another little bit of complexity on top of it. I don't have enough patience. Do you trust that this will work? We'll take a look later. So, to get into parallelization, what we're going to do is we're going to write a function to handle each observational unit separately. The key requirement in parallelization here is that the function is able to handle, so you're able to break it up into independent parts. So for example, if this is an ODE for patients, each patient is independent. Here in this harmonic oscillator, each observational unit is independent of the others. Right? So that's the level that we're going to loop over. We're going to pass that function into the map_rec function. And what this does is it's going to do like a map reduce type of thing where it'll map all the arguments in there and pass it off, and hopefully be able to run each of those things independently on separate cores or on separate boxes if it's necessary. In this version today, all the data is rectangular, so we'll need a pad out if you have any ragged data. What I mean by that is if the first observation you had 20 time points and the second one you had 10 and third you had 20, you have to pass it rectangular data structure, so you'll have to pass it 20, 20, 20, even though the second one only has 10 items. And from the language, this is all that's necessary. We can write a model that uses maprect. You don't actually need to enable anything on your computer in order to do this. When we go to build the program, that's when we'll need to have separate build instructions that enable it. So based on how you build the program will depend how it's run. So it'll either run in serial or run in parallel. So the function that we need to write for the observational unit has this function signature, and it, just like the ODE function, it has to match this. There's no other option. So the first is a vector, and that's going to be shared parameters across all the computation. We'll walk through that a little bit. Second vector is the individual parameters. In the ODE, both of these would have been all included inside the theta function, or sorry, the theta argument. So what we're doing is breaking up the theta into things that are shared and things that are per individual. And the next two arguments just match the arguments in the ODE, a real data and a integer data. And the return is vector. This return type allows us to have the flexibility to return what we want. So we could return the states of the ODE. We could already compute the log density, sum it all up, and just return a single value if we wanted. It depends on what you want to do. For this example, we'll return back the states as a vectorized, just concatenated. And this function will handle each observational unit. Right? And what we do is we pass this into this function called maprect, and that function is passed in as the first argument, the name of the function. There's this vector phi, which is the shared parameters. So that's just one vector that gets passed to the function every time. Vector thetas has, in our case, n should be it should be an n vector. So there should be an array of n vectors. An n array of vectors, sorry. So each of those will be passed off to f along with this XRs. So the first index is going to be capital N, and data, the first index is going to be capital N. What Stan's going to do is it's going to loop over all these parameters of this argument, split it off, and then put it into F, and then concatenate all the output into one vector. So let's write the function for one observation. Right? So this is it. So the return type's vector, I've called it individual ODE. There's a vector phi, a vector theta, real XR, and int xi. Right? What I've done is inside here, I've included the t as my first xi variable, or xi, first element in there. And then I'm just going to call integrate ODE with the XR1, 2, that's going to be my initial conditions. And then 0.0, I could have passed that in as XR3 and then shifted all these, but what I did was just hard-coded 0.0. And the rest of the times are here. Thetas are, since the theta is a vector, I need to change it to an array. So So I just use this 2 array 1D. And then these don't matter, so I just pass an XR and XI. I could have been a little more clever, but didn't need to. And when I return, what I'm going to take is I'm going to take the output that I'm used to, this real y t comma 2, and I'm going to slice off the first column and change it into a vector, slice off the second column, change that into a vector, and append them together. So it's one long vector with the first set of elements, the second set of elements. I could have done this in any other number of ways. I could have done row by row. I could have gone backwards if I wanted, but to me this makes sense, so that's what I did. You'll notice that we're still calling integrate ODE BDF in here, and the return is a single vector. Right. So if you want to see this, we can look at show underscore fit underscore multiple parallel start dot stand. This doesn't quite get all the way to the map rect. This exercise is using this integrate individual ODE function. And the differences here are really setting up the data. We have an xi, which is an array of length n, and xr, which is n by t plus 2, which has the first two elements here are going to be y naught, the initial condition, and the next elements are going to be the times. Right. Just so here I'm looping over each of the individuals. My return type is a vector, and we know that's t by 2, so t times 2 is a size, and I call the individual ODE. Phi here is nothing, and I pass in the n, xr, and xi, and then what I do is I reconstitute my y like before, just by slicing off and calling 2 array 1D. All right, questions? It's pretty clear. Once we do that, the rest of the model is exactly the same. We haven't changed any of this. Okay. Okay, so the final thing is using maprect. So instead of looping over each of the individuals here, we're going to make one function call to maprect, and that'll take care of everything for us, and we're still responsible for unpacking. And what does that mean? So the functions block is still the same. We haven't touched that. The data is still the same. The transform data is the same as the one right before. And here in transform parameters, instead of looping over the individual ODEs, we're going to pass that to maprect. The first argument is the function that we want to map over. The second phi is the one, there's the parameters that are shared across all the individuals. Theta here is of size, it's a vector 1, but we have n of them. So we're gonna, for each individual ODE, we're just gonna look at one of these vectors and pass it in, right? So each of them are gonna run independently. XR has a very similar flavor where there's this big index n out in front. Same with XI. And that one call will return back this n times 2 t times 2 sized vector. And we know exactly how that's packed because we decided what order everything was going to come out in. And, you know, this is just to loop through and unpack it.
So just checking that map rect is a parallel now.
So maprect in the Stan language
Yeah.
is agnostic whether it's parallel or not.
Yeah.
It's when you build it that you decide whether or not it's going to be run using threading, using MPI, or using a single core.
Okay, so it's on the command line.
Yeah. Let's see. Equals. So just to, I'm just going to run this. This is in parallel.
So where's the thing that says parallel?
Okay, so actually I have a couple more slides. Maybe that'll clear it up. Okay, so enable, for this example, if you're following along, we can do this, especially if you're on Linux or Mac. We're going to enable threading. We're not going to enable MPI right now. MPI is very, very similar. The reason is to build MPI, you actually have to get a few more dependencies. Threading is a lot easier to set up. So if you're running this with me, all you have to do is open a file, put it inside a file called make/local, and it won't have a file extension. And we're just going to add these flags, CXX flags plus equals minus D stan threads, and that enables the compilation to go with threading. So that's within command stan, so make local, and that's what I have inside my make local. All right, so next you have to actually build the program. I've already built it before, so what I had to do is trick make into thinking that I've touched the file, I've changed the file. That's what that does, and then this, I just build it like I would normally build it. And once I do that, it automatically builds it with the threading available. And then when I run it, I want to set the stan num threads to a number. -1 in this case will use as many cores as you have, and any number positive will be that.
Does that count virtual cores or not?
It does count virtual cores.
I think we should turn all that logical stuff off.
Okay, we can. Okay, so to show you this thing running, so first I'll CP show fit multiple parallel to just call it threaded. Okay, so what I did was I copied the thread version into this thing called show fit threaded. Export stan num threads equals -1. Threaded. I'm going to time that. We're going to sample data file equals .data.r. It's 10, just so we can see the output, and file equals threaded.csv, just so we can reproduce it. Seed equals 1, 2, 3. All right, so we'll kick that off. And it's probably really hard to see, but right now it's running with 8 threads. It's this thing up here, 7 threads. since there are 10 ends, like the big N was 10, and I only have 8 virtual cores on here, it'll use 8 and then run it with 2. So while that's going, are there any questions? It's running.
Is Stan got its own threading? Does Stan have its own threading?
The question is, does Stan have its own threading library?
Okay.
Yeah, we're just using C++11 threads.
Yeah, this is very simple to synchronize because the parallelism is just shipping off some parameters, running independently, and then shipping some gradients back. So it's a pretty easy synchronization model because the whole thing's pretty embarrassingly parallelizable.
So this is like, they're totally independent, right? Like you're just sharing the compiled model, and this is in lieu of what, like running like 10 different copies of the executable on the same machine? Or are they actually sharing information between each data set?
Here in this particular model, there isn't anything shared, but you can imagine something like, let's say we had something like,
I think the simple answer to your question is that this makes a single chain faster. So it's ideal if you have something that takes 3 days to run, but you happen to have 100 processors lying around.
That explains this. The nice thing to me once was just that, like in the expression graph, you start here with point, point, point. Everything below each of those places you would then parallelize.
Yes.
So they're just all independent. You can't have things joining into each other.
Paul?
Yeah, the map rect encapsulates that independence.
Yep.
Did you say that we cannot use the CX from parser and Python? So is that part of Python 2018? I'm not sure. I managed to put it into Python.
I don't know. The question is whether or not it'll be available in RStan and PyStan 2.18. I don't know. Bob, do you have any sense?
Yeah, I actually don't know either. Because we mainly targeted building this just for Linux command line stuff, but then the threading stuff turns out to run on Windows and everything else, whereas MPI is a real pain to get running. So the threading should work everywhere. I don't know how they're going to instrument it in PyStan, or in RStan to get it configured like this, but
it shouldn't be too difficult, right? So if you can run it.
no, it should totally be possible. It's just we haven't released RStan 2.18 yet.
No, I was just looking for documentation.
Yeah.
Yeah.
Whereas
I was thinking, I'll read about it.
PyStan 2.18 just came out, and I'm not sure exactly what they did.
So all this is in the 2.18 manual.
Yes.
I guess I can build.
Yeah, I think we probably released it somewhere. It's taken us a long time to get the interfaces out this time.
Just so you
Because
know,
of all this MPI, threading, and everything else going on.
in real time, that took 2 minutes and 40 seconds using my computer, and I just kicked it off with the other one, and we'll see if it finishes by the time we're done. Just a few more minutes. All right, certain things that we didn't cover, ragged data. I know I mentioned it. To use it inside MapRect, you have to pad it out. You have to pad out each of those data structures because they're all rectangular. That's where the rect comes from. Censoring, that's just part of the model. Like for example, if you have censored data, if for some reason you knew that there are data points in this quadrant, but you don't know where inside the quadrant it is, that's not a big deal. You can just write a model to do censoring. So that has no effect on how you write your ODE. It's just how you write your likelihood term. We didn't cover a lot of speeding up the code. You know, the ODE function gets used a lot. It gets called many, many times to do the solving. So obviously, if you do things inefficiently within that function, it's just going to reflect on how slow it goes. There are other tricks, like you can reparameterize the ODE itself, like do it on the log space if you are very careful with your math. And debugging through an ODE didn't cover, but it makes it a little more challenging than just debugging through just a regular Stan program without an ODE. And part of the reason is it's slow. Second, you have to understand whether or not the ODE solutions are just going off the rails because you're in a bad parameter space, or whether or not you implemented the ODE correctly or incorrectly. Right, so there are a lot more complicated issues here, but otherwise it's all doable. Still going. I think it's been 3 minutes, so it's you know, obviously it's going to take longer to do it single core. That's it. Thank you.